Something unusual is currently moving through our solar system, an object designated 3I/Atlas, believed to be an interstellar comet. It did not originate from our Sun's planetary system, but instead appears to have come from deep space between the stars. Detected by automated sky surveys, it quickly stood out because of its extreme speed and its trajectory, which does not form a closed orbit around the Sun. Instead, it follows a hyperbolic path, meaning it will pass through once and never return. That alone places it in an extremely rare category. Only a few such interstellar visitors have ever been confirmed. What makes 3I/Atlas particularly interesting is not just its origin, but its behavior as it travels through the inner solar system. As it approaches the Sun, it begins to show signs of activity typical of a comet, such as the development of a surrounding cloud of gas and dust called a coma. This happens when surface materials heat up and begin to sublimate directly from solid ice into gas. However, observations suggest that this object becomes active at distances where most comets remain largely inert, implying that its composition may be different from the comets we are used to seeing. As sunlight interacts with the material being released, the object also becomes brighter, but not always in a smooth or predictable way. Instead, its brightness appears to fluctuate, suggesting bursts of activity rather than steady outgassing. This behavior raises questions about its internal structure, whether it contains pockets of volatile material, layered composition, or surface regions that react differently to solar heating. Scientists analyze changes in brightness, gas composition, and reflected light to understand what it is made of, but the data so far does not match the patterns of typical solar system comets. Another unusual feature is the composition of the gas detected around it. In similar objects, water vapor is usually dominant, but in this case, other gases such as carbon dioxide appear unusually prominent at earlier stages of its approach. This suggests it may have formed in a much colder environment than most known comets, possibly around another star where chemical conditions were very different from those in our solar system. Over time, as it gets closer to the Sun, additional materials are expected to sublimate, potentially revealing more about its internal structure. The importance of 3I/Atlas lies in what it represents, a physical sample from another planetary system passing through our own. Unlike distant exoplanets that we can only observe through telescopes, this object can be studied directly as it releases material into space. It offers a rare opportunity to compare the building blocks of other star systems with our own, helping scientists understand whether the ingredients for comets, planets, and possibly life are common across the galaxy or unique to certain environments. Once it leaves the solar system, it will not return, making this short observation window the only chance to study it up close. As 3I/Atlas continues its passage through the inner solar system, scientists are focusing heavily on what it is actually made of. This is where the object becomes even more interesting, because its chemical signature does not fully match what we typically see in comets formed around our Sun. One of the most important clues comes from the types of gases detected in its coma. Instead of behaving like a water-dominated comet, which is the norm for most icy bodies in our solar system, 3I/Atlas appears to release a much higher proportion of carbon-based gases at earlier stages of heating. Carbon dioxide in particular seems unusually abundant, suggesting that the object may have formed in an environment far colder than the region where most of our own comets originated. This matters because the composition of a comet preserves information about the temperature and chemical conditions of the system where it was born. Water ice, carbon dioxide ice, carbon monoxide, and other frozen volatiles do not form or survive equally under all conditions. The ratios between them act like a fingerprint. In the case of 3I/Atlas, that fingerprint suggests formation in a region where carbon dioxide ice could remain stable for long periods, likely far from any star, or within a much colder protoplanetary disk than the one that formed our solar system. That alone points to a very different kind of planetary nursery. Another key detail comes from how the object evolves as it warms up. As it approaches the Sun, different layers of material begin to activate at different times. Early observations show carbon dioxide driving most of the activity, but later measurements begin to reveal increasing amounts of water vapor. This shift suggests a layered structure, where volatile materials are not evenly mixed, but instead separated by depth or composition. It's similar to peeling back layers of time, each layer responding differently as solar energy penetrates deeper into the object. Even more intriguing are the trace elements found in the surrounding gas. Small amounts of metals, including nickel, have been detected, but their behavior does not always match expectations. In most comets, metals appear alongside other elements in relatively predictable ratios, because they originate from the same early formation processes. But with 3I/Atlas, the timing and proportions appear unusual, as if certain elements are being released independently or under different conditions than expected. Scientists are still trying to determine whether this is due to the object's original composition or the way solar heating is interacting with its surface. All of this feeds into a larger question: how representative is 3I/Atlas of other planetary systems? If its composition is truly different from most comets in our solar system, it may suggest that the chemistry of planet formation varies more widely across the galaxy than previously thought. That would mean the building blocks of planets, and potentially the conditions for habitability, are not uniform. Instead, they may depend heavily on the environment in which a system forms, including temperature, radiation levels, and the local abundance of elements. At the same time, scientists are cautious. One interstellar object is not enough to draw broad conclusions about the galaxy. It is possible that 3I/Atlas is unusual even by interstellar standards, shaped by rare events during its long journey between stars. Over millions or even billions of years, exposure to radiation, collisions with dust, and gravitational encounters could all alter its surface and composition. What we are seeing now may not perfectly represent where it originally formed. Still, every new measurement adds another piece to the puzzle. And because we only get a short window to observe it before it leaves forever, researchers are collecting as much data as possible while it is still close enough to study. In many ways, 3I/Atlas is less like a stable object and more like a traveling archive, one that is slowly revealing its contents as it moves through sunlight for the first time in possibly billions of years. The next major question surrounding 3I/Atlas is not just what it is made of, but where it actually came from. Unlike objects that originate in our solar system, which can often be traced back to the asteroid belt or Kuiper belt through orbital modeling, interstellar objects are far more difficult to pin down. Once something is ejected from its original star system, it begins a long, unplanned journey through the galaxy, influenced by countless gravitational interactions along the way. Over millions or even billions of years, its path becomes increasingly complex, making any precise reconstruction nearly impossible. Even so, astronomers can still work backward in a statistical sense. By mapping its current velocity and direction, they can estimate where it likely entered our solar system from. In the case of 3I/Atlas, that incoming direction appears to align broadly with the dense central region of the Milky Way. This doesn't mean it originated from the galactic center itself, but rather that it may have traveled through or near that direction at some point in its long history. That region is rich in stars, meaning gravitational encounters are more frequent, and objects are more likely to be scattered into interstellar space. Some models suggest that objects like this may be extremely ancient. If 3I/Atlas formed in a distant star system and was later ejected, it could have spent billions of years drifting through interstellar space before finally entering our neighborhood. During that time, it would have experienced extreme cold, cosmic radiation, and occasional gravitational nudges from passing stars or molecular clouds. Each of these interactions could slightly alter its trajectory, meaning the object we see today is the result of a very long and chaotic journey. Another important aspect is its unusually high speed relative to the Sun. While all interstellar objects move quickly compared to bound solar system bodies, 3I/Atlas appears to be traveling at the higher end of the observed range. This suggests it may not have been gently ejected from its original system, but instead may have been propelled by a more violent event, such as a close planetary encounter or gravitational interaction with a large gas giant. In some cases, objects can even be accelerated during multi-body interactions, gaining enough energy to escape their star system entirely. Because of these uncertainties, scientists cannot confidently link 3I/Atlas to any specific star or region of origin. Unlike comet families in our solar system, which often share common orbital characteristics and can be traced back to shared sources, interstellar objects arrive as isolated cases with no clear family history. Each one is effectively a standalone sample from somewhere else in the galaxy. What makes this especially fascinating is that even if we cannot identify its exact origin, we can still learn about the environments it passed through. Over time, interstellar objects accumulate subtle changes: erosion from cosmic rays, surface chemistry shifts from radiation exposure, and possible structural weakening from thermal cycling. In that sense, 3I/Atlas is not just a snapshot of its birthplace, but also a record of its entire journey. This is why its discovery is so valuable. It is not simply a rock from another star system, it is a long-traveled object that has survived conditions far harsher and more varied than anything in our immediate cosmic environment. And every new observation helps refine our understanding of how material moves through the galaxy, how often star systems exchange debris, and how interconnected planetary systems might actually be over astronomical timescales. As it continues its path outward, 3I/Atlas will eventually fade from view again, returning to interstellar space. But the data collected during its brief passage will remain, helping scientists compare it to future interstellar visitors. And with each new detection, the picture of our galaxy becomes a little less isolated, and a little more dynamic. By this point, it's impossible to talk about 3I/Atlas without comparing it to the two interstellar objects that came before it, 1I/ʻOumuamua and 2I/Borisov. These earlier discoveries are what first proved that interstellar objects are not just theoretical, they are real, and they pass through our solar system more often than we once believed. But each one has told a very different story, and 3I/Atlas adds yet another variation to that growing list. ʻOumuamua, discovered in 2017, was the first. It immediately became controversial because it didn't behave like a normal comet or asteroid. It showed no obvious coma, no clear outgassing, and yet it still exhibited non-gravitational acceleration as it moved away from the Sun. That led to a wide range of hypotheses, from unusual natural processes to more speculative ideas. But despite years of discussion, no single explanation fully resolved all of its strange properties. What it did accomplish, however, was reset expectations. After ʻOumuamua, scientists had to seriously consider that interstellar objects might not always look familiar. Then came 2I/Borisov in 2019, which was almost the opposite case. It behaved like a textbook comet. It developed a coma, released gas and dust in predictable ways, and followed dynamics that matched what we already understood. In a sense, Borisov was reassuring. It confirmed that at least some interstellar objects are chemically similar to comets in our own solar system. If ʻOumuamua raised questions, Borisov temporarily restored balance. Now 3I/Atlas sits somewhere in between those two extremes. It does not appear as unusual as ʻOumuamua in its motion or structure, but it also does not behave as cleanly as Borisov. Instead, it shows a mix of expected and unexpected characteristics. Its early activity at large distances, its unusual gas ratios, and its changing coma composition all suggest a more complex object than a standard comet. At the same time, its overall trajectory and general behavior still fit within the framework of natural interstellar objects. This middle position is what makes it so scientifically interesting. Rather than being an outlier that challenges every model, or a perfect confirmation of existing ones, it forces scientists to refine the range in between. It suggests that interstellar objects may exist on a spectrum, some relatively normal, others chemically or physically unusual, and many that fall somewhere in the middle but still carry unique signatures of their origin systems. Another key difference is how long we are able to observe 3I/Atlas compared to its predecessors. ʻOumuamua was discovered after it had already passed its closest point to the Sun, meaning astronomers had limited time to gather data before it faded from view. Borisov was observed earlier and more clearly, but still had a relatively short observation window. In contrast, 3I/Atlas has been tracked across a broader portion of its journey, allowing for more detailed monitoring of how it changes over time as it is heated by the Sun. That time element is crucial. Comets are not static objects, they evolve rapidly when exposed to solar radiation. Surface layers erode, new materials are exposed, and outgassing patterns shift. Watching that process in an interstellar object gives scientists a rare opportunity to see how materials formed around another star respond under the conditions of our own. There is also a larger implication behind all of this comparison work. With only 3 confirmed interstellar objects so far, every new detection dramatically expands the dataset. It is still too small to draw firm statistical conclusions, but patterns are beginning to emerge. Some interstellar objects are rocky, some are icy, some are active, and some are nearly inert. That diversity suggests that planetary systems across the galaxy may produce a wide variety of small bodies, and that the process of ejecting them into interstellar space is common. In other words, our solar system is not isolated in its debris. It is part of a much larger exchange system, where material is constantly being launched into the galaxy and occasionally passes through other systems like ours. 3I/Atlas is one more data point in that emerging picture. And while it may not provide definitive answers on its own, it strengthens the idea that interstellar space is not empty. It is populated with remnants of planetary formation, traveling endlessly between stars, waiting for brief moments of observation before continuing their journey into darkness once again. As 3I/Atlas moves past its closest approach to the Sun, the focus shifts from discovery to interpretation. This is the point where the object stops being something we are finding, and becomes something we are actively trying to understand based on limited, fading data. Its brightness begins to change again as it travels outward, and the same solar energy that once triggered intense activity now starts to weaken. The coma, if still present, gradually thins. The outgassing slows. And slowly, the object returns to the quiet state it likely maintained for millions or billions of years between star systems. But what remains is the data, and the questions that come with it. One of the biggest scientific takeaways is simply confirmation that interstellar objects like this are not rare anomalies. They are part of a larger population of material constantly moving through the galaxy. Every star system likely ejects debris during its formation and evolution. Planetary migration, gravitational instability, and close encounters between large bodies all contribute to scattering material into interstellar space. Over time, that debris accumulates into a vast, invisible background population of objects like 3I/Atlas, drifting silently until one of them happens to cross our observational path. The second major takeaway is compositional diversity. Each interstellar object discovered so far has shown a different personality. ʻOumuamua appeared dry and elongated with unusual acceleration. Borisov behaved like a familiar comet with a recognizable chemical signature. And 3I/Atlas shows a more complex, evolving chemistry that doesn't fit neatly into either category. Together, they suggest that there is no single, standard type of comet or asteroid in the galaxy. Instead, there are many variations shaped by local conditions in their birth systems. That idea has deep implications for planetary science. If small bodies vary this much between star systems, then the building blocks of planets may also vary more than previously assumed. The ratio of water to carbon compounds, the abundance of metals, and the structure of icy materials could all differ depending on where and how a system formed. That doesn't just affect comets, it affects the entire chemical environment in which planets develop. There is also the question of time. 3I/Atlas may be extremely old, potentially predating Earth itself. If that is the case, then what we are observing is not just material from another star system, but material that has survived an extraordinary journey through cosmic time. It has endured radiation, temperature extremes, and gravitational perturbations across interstellar distances. That makes it less like a single snapshot and more like a surviving fragment of a much larger, long-lost population of early planetary material in the galaxy. And yet, despite all of this, the most important part of 3I/Atlas may not be what it tells us directly, but what it represents for the future. We are only at the beginning of detecting interstellar visitors. Improved sky surveys, better detection algorithms, and more sensitive telescopes mean that objects like this will likely become more common discoveries in the coming decades. What once seemed like a once-in-a-lifetime event is now becoming a new category of routine observation in astronomy. That changes everything. Instead of relying on a single object every few years, scientists may soon be able to compare dozens or even hundreds of interstellar bodies. Patterns will become clearer. Outliers will stand out more sharply. And eventually, we may be able to map not just individual objects, but the broader flow of material through the galaxy. For now, though, 3I/Atlas is still just one object, fading as it leaves, carrying its secrets back into interstellar space. We will not see it again. No spacecraft will reach it. No second-chance observations will be possible. All we are left with is a short window of light, a stream of data, and a set of measurements taken while it briefly passed through our neighborhood. And in that sense, it serves as a reminder of something fundamental about astronomy itself: we are not studying objects that wait for us. We are studying events that happen whether we are ready or not. 3I/Atlas passed through our solar system on its own timeline. We simply happen to be watching. As 3I/Atlas continues its journey outward, it slowly slips back into the darkness it came from. Its brightness fades, its activity declines, and within a relatively short astronomical window, it will become just another invisible object moving between the stars. No telescope will be able to follow it for long. No mission will intercept it. And eventually, it will be lost again to interstellar space, possibly forever. But what does not fade is what we learned from it. For the first time, we've been able to observe an interstellar object not just as a passing point of light, but as a changing physical system. We watched it brighten, we watched it release gas, and we watched its chemistry evolve as it responded to the sun. Even if our understanding is still incomplete, the data itself is permanent. It becomes part of a growing archive of interstellar visitors that will eventually define how we understand material from beyond our solar system. And that leads to a bigger realization. Objects like 3I/Atlas are not rare exceptions, they are part of a constant cosmic exchange. Every star system likely sends out material, and every star system likely receives it. The galaxy is not made of isolated islands. It is more like a network of overlapping paths, where debris, dust, and icy bodies drift endlessly between worlds. Most of it will never be noticed. But occasionally, one of those travelers passes close enough for us to see. 3I/Atlas was one of those moments. It also highlights something subtle but important about scientific discovery itself. We do not always understand what we are looking at when we first observe it. ʻOumuamua challenged assumptions. Borisov confirmed some of them. And 3I/Atlas is currently expanding the middle ground between those two extremes. Each object doesn't just add information, it reshapes expectations for the next one. Because there will be a next one. With modern sky surveys constantly scanning the entire night sky, interstellar detections are becoming more frequent. What once seemed like extremely rare cosmic events are now expected to become part of routine astronomical observation. In the coming years, we may move from studying single examples to building entire populations of interstellar objects, comparing their chemistry, motion, and structure across dozens of cases. And when that happens, 3I/Atlas will not just be another distant memory. It will be one of the early reference points, a stepping stone in our understanding of how planetary systems across the galaxy form, evolve, and occasionally shed fragments into the void. For now, though, it is gone from view. No longer bright enough to track easily. No longer active enough to study in detail. Just continuing its path outward, back into interstellar space, carrying with it whatever secrets it has not yet revealed. And in the end, that may be the most important lesson of all. We are not just observing the universe from a distance. We are part of a system where worlds exchange material across unimaginable gaps in space, and every once in a while, one of those travelers stops long enough for us to notice. Then it leaves again. And we wait for the next one.